Hi everyone. In this talk, we'll discuss why LLVM IR has a problem with lowering chars as integers, why is it bad, and how we can fix it. First, let's talk about LLVM's memory model, pointers and integers in more detail. As the language reference says, LLVM IR doesn't associate memory with types, and every read and write to memory uses type information purely for size, alignment, and value interpretation. So this makes us conclude that the memory in LLVM is untyped. But the question is it really untyped? And what we can try to do is to formally argue whether the memory is untyped or not. And initially suppose that it is indeed. And since the memory is untyped, then any load or store of any type is equivalent of loading or storing an integer of appropriate size. So essentially, a sequence of bits is stored to memory, and then a sequence of bits is retrieved from memory. So as shown in a simple example here, we have two functions, foo and bar, and they should be equivalent under untyped memory model. Foo stores the char pointer to memory, and bar reinterprets the pointer as an integer, i.e. a sequence of bits, and stores the sequence to memory. But then storing a pointer to memory is equivalent to storing its integer representation. So integers must be the same as pointers. And well, that's not exactly true. While integer has it's just a sequence of bits that are interpreted as some numerical value, pointers are more than that. Yes, they carry an integer that represents a memory address, as well as some special metadata. For example, they carry provenance, a set of all objects that can be accessed through the given pointer. And the problem is that when we cast a pointer to an integer, we only keep the address information, but lose the provenance. Now let's see how losing provenance contradicts the untyped memory model. Consider a function foo that takes a pointer p. And let's suppose that we store some value to p, and then store p itself on the stack. Then what we're going to do, we're going to load it back from memory. But this time we will use type tuning and load it as an integer instead. Since memory is untyped by our assumption, strictly speaking, we do not know what was the type of this p as int in memory. And we simply interpret it as an integer. And then we can do simple integer comparison, which is if evaluated true, calls bar function with a value equal to p as int. But let's not forget that p as int is an integer representation of a pointer, and therefore it has no provenance. And therefore, when we call bar function, it can change memory at the address specified by p as int without the compiler realizing that the pointer escapes, because it relies on alias analysis, which relies on tracking of the provenance. So essentially what we have is a contradiction. If the memory is untyped, then any integer load is equivalent to a pointer load. However, it's not true because integers don't have provenance and they're not equal to pointers as we've just shown. Moreover, the situation gets worse if we consider the semantics of unsigned char in C. In LLVM, it is just an integer, and therefore it doesn't carry any provenance. While in C, unsigned char also represents raw memory, and therefore can carry pointers that have provenance and can move them around, preserving the provenance. With this contradiction and kind of clear semantics inconsistency, we can ask ourselves, how bad is it? And as you might have guessed, it's quite bad, and otherwise I wouldn't be here presenting. So let's consider a motivational miscompilation example. So suppose we have two arrays of size 4, p and q, and let's suppose that it happened and p immediately follows q. This condition can easily be checked by this snippet of code, where we compare an address of p0 with an address of q4. Importantly, note that taking an address of q4 is not undefined behavior, because the C standard specifies that it's legal to take an address of 1 plus the n element of an array. Now, we would like to store 10 to p0 using our specially handcrafted function, which we call store 10 to p. And then we want to print the contents of p0, which should be 10, obviously. We call this function with two pointers that point to the same location memory, but belong to different objects, and thus have different provenances, which is p0 and q4. Now, let's take a closer look at what our function does. So it takes two pointers, p and q, as arguments. Recall that due to condition of p immediately following q, both p and q point to the same location memory. However, they belong to two different objects and cannot be interchanged freely. Then, what we can do, we can interpret both pointers as raw data, which in C can be done by a simple memcpy into an array of unsigned char. And then, following the type tuning, we define another array of unsigned char that we call buffer, to which we will copy data byte per byte. In the body of the for loop, we get the integer representation of an ith byte of pointers p and q. But since they point to the same location and have the same address, essentially, they have the same integer representation. So c1 is always equal to c2. And then we store an ith byte of pointer p into buffer in a quite elaborate way. This conditional always evaluates true because c1, as we've already established, is always the same as c2, and therefore we only copy pointer p. Then we can define a pointer r and copy the contents of buffer, which is now p, to r. So essentially r becomes p, and it points to the same address and has the same provenance, so it points to the same object. Then we store 1 to p, and then the store is followed by another store of 10 to r. But since r is the same as p, we actually store 10 to p, making p0 to be 10. Right, so that was a quick walkthrough of our example. So let's compile the code with Clang and see what we have at p0 in reality. Compiling with no optimizations on, unsurprisingly, gives us 10. But let's see what if we turn on some optimizations. But yeah, when we compile at 03, it turns out that p0 is actually 1, which is a bit weird. So let's find out why did this miscompilation happen. And we'll try to analyze it step by step. So first, inscombine has an integer optimization that removes an if-else statement of the form if x is equal to y, then x else y, and replaces it with y. So this leaves us with a simple store of ith byte to q to the buffer array instead of the whole conditional. Then LLVM also has a loop idiom recognizer that looks at this for loop and realizes that that's actually a simple memcpy. So we should go forward and replace it with a memcpy function call. Then, since the size of pointer q is quite small, so usually 64 bits on some platforms, inscombine has another optimization that transforms a small memcpy call to an integer load store pair. And applying these optimizations to two memcopies that we have here, we essentially have the following sequence of loads and stores. This is not quite C anymore, but I hope you see what is going on if you think of this as LLVM IR code. Then we can analyze the data flow of the sequence of loads and stores, and we see that we actually load from Q that we later store to buffer, then we load from buffer again, and then we store to R. So this seems to be a perfect candidate for integer store forwarding, which essentially gets us the following. Now we store Q to R, and therefore R is equal to Q, not to P. And as a result, optimizer thinks that storing to R does not affect P because R is Q now, it has different provenance, and therefore alias analysis doesn't really realize that we stored to the same location. And in the end, we get the value of 1 in P0. Wow, that was quite unfortunate. So what actually went wrong in our example? Well, there are a number of things and a number of problems, but mostly all of them boil down to the same simple fact, is that the semantics of char is not the same as semantics of I8. Chars are universal type holders in C and can carry any data. If unsigned char carries a pointer, it preserves its provenance. In LLVM, on the contrary, integers are being used as universal type carriers. But as we've already seen, integers are not equal to pointers, and they don't carry any provenance as well. And because of this inconsistency, certain LLVM integer optimizations are invalidated, like equality propagation in InstCombine and GVN, as we've already seen. So yeah, this seems quite bad. I guess you can agree. And the question is, can this happen in Linux kernel? Well, potentially yes. So we definitely need to fix it. And another question we might want to ask is if there is some conservative solution that doesn't require many changes that we can quickly patch. And well, we can try to find one. A simple solution is to keep everything as is. We keep the memory untyped. And for every optimization that is not sound when integers can carry pointers, we just disable it. For example, propagation of integer equality can be disabled, and multiple other optimizations can be disabled as well. So clearly there are obvious advantages of this approach, like low engineering effort and the fact that we preserve the same IR. But on the other hand, there are significant drawbacks with this approach. Not only we get a performance regression because we disable important integer optimizations, but we're also not guaranteed that the issue will not reappear somewhere else in the future. So the next question would be, is there another way to solve it? Well, yes, there is a possible solution. It is basically to change the way Clang lowers unsigned char and char to preserve this raw data access properties and semantics. And this essentially means that we want to make memory typed. One of the solutions that was actually proposed by other LLVM developers was to annotate potential raw data loads and stores with some special flags. Then a simple memcpy optimization we mentioned before can look like something like this, essentially. Then the optimizer can check for the flags to deduce if integer potentially carries a pointer, and if it does, then be more conservative with subsequent optimizations. So apart from the fact that we should stop adding attributes to LLVM, as John Rager said in his talk earlier, there are multiple problems. First, we would need to annotate every char load in C or C++ with flags. And secondly, every instruction in the data flow path that uses the result of instructions that are annotated must be annotated as well. We then find ourselves asking what additional raw data or select over raw data can potentially mean, and there's no clear answer about that. So let's put this disadvantage aside and let's think about implementations. So there are two ways in which we can implement this. First, we can be conservative. We can add attributes or these flags everywhere and change optimizations to be conservative when they encounter these flags. That's quite good because we can then gradually make optimizations more aggressive, but then performance regressions apply. So that's not what we want, ideally. On the contrary, we can be aggressive from the start. We add attributes only where needed, and then we find optimizations that need to take this raw data flags into account, and we fix them. The only question is, how do we find which optimizations we need to fix? Where do we need to check for these flags? And the answer is, there is no easy way to find it out. That's why we propose to add a new type, which we call a byte type. So unlike the annotations approach, we define a byte type to be a first-class type that represents raw data. So you can think of it as a kind of unsigned char in LLVM IR. This type is under the same optimization restrictions as pointers and carries provenance information if necessary implicitly. The benefit of adding a new type, apart from just aesthetics, is that we can be aggressive. The probability that asserts in LLVM codebase and easy checks fail with this new type is way higher. This means that it's much easier to identify failing and unsound optimizations when we change the lowering of unsigned char to byte instead of integers. This reduces the frequency of silent miscompilations due to flags, like this raw data flag, being ignored. Are there any disadvantages? Well, we changed the memory model of LLVM IR, making it typed, and we also need to fix all unsound and failing optimizations. And when we introduce a first-class type, then surely there's going to be a lot to fix. So this work requires significant effort to be introduced to LLVM. But importantly, I think that the safety that we get due to explicit assert and easy check failures outweighs all the cons. And apart from that, it's not that much work after all. During Google Summer of Code this year, which was actually part-time, we implemented a prototype. And now we would like to share our initial results. So what we did, we introduced a new family of byte types to LLVM, as well as a new instruction to convert byte types to other types and then other types to bytes. Moreover, we changed clang to emit byte types for char and unsigned char. In selection tag, currently we lower byte types to just integers. Finally, we also fixed wrong optimizations, like this transformation of a small memcpy into pair of integer load and store. Now, memcpy is transformed into byte load and store. In addition to that, we had to fix a number of optimizations that were failing because of this new type. So, for example, SLP vectorizer didn't know how to vectorize byte conversion instructions. And lastly, we measured performance. We measured compile time, execution time, and the size of the final binary, comparing them to metrics collected from LLVM trunk version. We observed very few performance regressions, as you can see in our first prototype, which is very promising. Some pending regressions have also been tracked down. For example, this 5% regression in execution time for excellency benchmark stems from a missed vectorization opportunity. Now, I guess it's a good time to conclude our talk because we're running a bit short on time. We hope that it was informative and everyone attending learned something new. But I guess the main takeaway message from this talk is that LLVM IR semantics is inconsistent. Currently, untyped memory model and integers cannot coexist together because integers cannot be universal type holders, because this invalidates certain LLVM optimizations that leads to miscompilations. We also propose a solution, a new first-class type that represents raw memory and follows the semantics of unsigned char in C roughly. Based on our performance evaluation on spec benchmark, our first prototype solution shows very promising results, which is good. Moreover, the engineering effort to implement turned out not to be that high. Over the summer, around 2,000 lines in LLVM subdirectory and around 100 lines in clang subdirectory were changed, obviously excluding tests, which is not that much. Then finally, what we need to upstream our work is to fix missing byte optimizations and this byte conversion instruction optimizations. And most importantly, we need to find a way to automatically fix failing tests in clang because of the new lowering from char or unsigned char to our new byte type. But of course, any contributions are always welcome, and we definitely need help for reviewing the patches. Hope everyone liked the talk. Thank you. Important thing to have in mind is that essentially what we try to do, we try to make LLVM IR sound, and the frequency of optimizations kicking in shouldn't be something that is really kind of a concern for us, because essentially we don't know when the miscompilation is going to strike, right? And if it's like happens in the Linux kernel, or if it happens in aircraft software. So we just want to make our IR sound, and we're not really kind of concerned about whether it's frequent or not.
Okay, thanks. Should we move on, or Nuno or Juneyoung, do either of you want to add to that? Okay, let's move on to a question from David Lloyd. The question is, how do the proposed byte types interoperate with opaque pointers?
Well, it's quite orthogonal to opaque pointers. It's a completely different thing. I think opaque pointers actually, they confirm that the pointy type has no semantic meaning, which is kind of a good thing. That's what we're trying to fix, essentially. The idea that LLVM memory is kind of typed.
Okay, thank you. Next question we'll take is one from Josh Cranmer. The question is, have you tried evaluating a more formal model of an escaping pointer analysis model to represent provenance instead of introducing a byte type?
So we were a bit short in time. It was in scope of Google Summer of Code project. So we did our analysis without it, evaluate different approaches, and we came up with a conclusion that introducing byte type is the most efficient way of trying to solve this problem, both theoretically and also in practice, or like engineering wise. If we had more time and more people that would help us, then like definitely would try to kind of try other options as well.
Great. Okay, the next question we'll take is from Jakub Kaderski. Would it help if we had an LLVM abstract machine and interpreter that did not implement pointers with integers? It's easy to get confused when every real-world hardware implements pointers using integers.
Well, yeah, that's a good question, but I think at this point we kind of have to live with the legacy stuff that has been done already. It's like, I mean, we still have C language, and many embedded systems are written in C, so we can't do anything about this at this point.
Okay. Let's take a question from Renato Golan, which is, what platform were these benchmarks run on?
Yeah, so we used ARM64 platform for that. That was available for us to run benchmarks. But ideally, yes, we would want to run benchmarks on other platforms to see how different architectures behave after our change.
Okay. And the next question is from Matthew Fernandez, and this is one that I actually had as well, so I'm glad it was asked here. Does some of this arguably stem from C lacking a proper byte type? That is, do you think ISO C should grow a byte type? And I think so I'll just add a tiny bit to this. The question is, how much of this mess did we inherit and how much of this mess did we create?
Yeah, that's indeed the question. But I mean, we can look at the C++ example. For example, in C++, they did add byte type. But the problem is that LLVM still loads as an integer. So it's not just about C having bytes and defining clear semantics and differentiating between types that access memory and types that are integers. So like making unsigned char to be just integer, for example, but also about LLVM being consistent with the semantics of the front end if necessary.
Okay, and we're about out of time here, so we can't really applaud very well here, but so I'll sort of clap for our speakers, and thanks a lot, guys.